Hello, AP Physics 1 students. This will be a lecture about electric charge. For Chapter 16 of your textbook, you'll notice in Chapter 16 that it includes some information about electric field. Electric field is beyond the scope of AP Physics 1. You will continue learning about electric field in AP Physics 2. So electric charge and charge interactions is also known as electrostatics. Electro, electric, electron, and statics, or not moving. So our focus is on how charges interact when they are not moving. So we find that things don't necessarily have to be touching in order for them to exert forces on each other. Our first experience with this is gravitational force. The Earth pulls on a bowling ball that's held above the Earth, and the pull causes the bowling ball to accelerate if we let it go. We then expanded that idea to include objects that are much further away from each other and are more similar in size, and we investigated the universal law of gravitation, G m1 m2 over r squared. That was even more of a non-contact, or we call it a field force. Now we're going to look at electric force. We're going to see how that is similar and different from gravitational force. So this should not be news to you, but it might be. The sort of general rules for electrostatics are that charge comes in two types, positive and negative charge, and like charges repel and opposite charges attract. The source of charge is the atom itself, so the subatomic particles that make up the atom. This is a very brief overview of the structure of an atom, and meant more as a reminder than actual lecture information. So you are hopefully already aware that the nucleus of the atom is very dense, very tightly packed at the center of the atom, and it's composed of positively charged protons and, for most atoms, neutrally charged neutrons. And that packed nucleus is surrounded by a very large, very low density electron cloud. In the diagram on the slide, you're seeing the orbital model of an electron, and that's fine for now, as long as you understand that those electrons are very far away from the nucleus and that they're opposite in sign from the nucleus. The electron and the proton are fundamentally different types of particles. But they happen to have the same amount of charge, just opposite in sign. So for every positive proton in an atom, when there's a negative electron surrounding that proton, the charge essentially cancels out, or under most circumstances cancels out, unless the atom or molecule is polarized. Matter on the whole is usually neutral, and that means there are equal numbers of electrons and protons in the atoms and molecules that make up the matter. So gaining an electric charge from a usually neutral atom can be done by physical contact between two different types of materials. The details of what I'm about to say are definitely the purview of chemistry or physical chemistry, but some atoms and molecules tend to have electron arrangements that allow them to lose an electron and still be sort of chemically stable. And some atoms and molecules have an electron arrangement that allows them to gain an extra electron and still be stable. So if we allow matter of those two types to be in contact with each other, electrons, because of that contact, will move from one substance to another. So that's called charging by contact. And we'll look at some examples of charging by contact in class. So in general, not just in general, some more rules of charge is that electric charge is conserved. So when we charge objects, we are moving electrons, and we're moving only electrons from one object to another. The sum of the total charge of the two objects that are having this charge interaction does not change. Another way to say this is that electrons are neither created nor destroyed in the charging process. So that word conserved we've used before in terms of energy. We said that in total, energy is not created or destroyed, but it can change forms and change from one system to another through work. Electrons are also conserved in a charging process. Electrons are neither created nor destroyed in the charging process. We also like to say that charge is quantized. That sounds fancy, but that simply means that we can only charge objects by adding or subtracting whole numbers of electrons. We're never charging objects with less than a single electron. So our first example question is, how many electrons make up a charge of negative 48 microcoulombs? So we go back to the idea that a single, which I didn't actually say on this slide, I just realized, a single electron has a charge of 1.602 times 10 to the negative 19th. Units of charge are coulombs. We'll talk more about that later. And as I said, electrons and protons have the same amount of charge. So we don't actually say positive or negative. We just use the symbol lowercase e for the sort of fundamental unit of charge on a single electron or proton. So our question again is, how many electrons make up a charge of negative 48 microcoulombs? Okay, so micro, curvy m, right? This is mu again, our friend mu from the Greek alphabet, means 10 to the negative 6. I often, and I think you might often also, confuse micro and milli. Milli, lowercase English letter m, is 10 to the negative 3. So 10 to the negative 6 is a very small number, but the charge on an electron is 10 to the negative 19th, an even smaller number. So we want to know how many times the charge of a single electron, so how many times whole number n times the charge of a single electron equals my total charge of negative 48 microcoulombs. How many times 1.602 times 10 to the negative 19th coulombs equals negative 48. The negative is really unnecessary because we know it's electrons, so I'm just going to drop that negative sign. So how many times this is equal to a total of 48 microcoulombs, right? Now I've sort of decoded my SI prefix, and I can actually divide both sides and have copacetic units. So I divide both sides by 1.602 times 10 to the 19th, and for this, I definitely need my calculator, which hopefully you'll be able to see. So 48, I need my power of 10 button on this calculator, times 10 to the negative 6 quantity divided by 1.602 times 10 to the negative 19th. And I've got, oh dear, that doesn't seem correct. Something went wrong in my calculation here. I wonder if I needed parentheses. That shouldn't be the case, but let's check it out. 48 times 10 to the negative 6. So the reason I knew that, oops, that didn't work, did it? Times 10 to the negative 6. So I'm expecting, oh, I think I see the problem. This calculator is a little bit tricky with powers of 10. I'm expecting a positive number, right? Because I'm dividing 10 to the negative 6th by 10 to the negative 19th. So I should get a lot of electrons. Oh dear, and look at that. I have a square here. We don't want that. Oh, for heaven's sake. You guys, I'm having a tough time. It's Thursday of the last week of the term. Thank you very much. But you're going to be watching this on your spring break. So hopefully you're laughing at me. There we go. 48 times 10 to the negative 6th divided by 1.602 times 10 to the negative 19th. Maybe I forgot to put the negative sign in there. And of course, I don't have enough editing skills to figure this out. There we go. So I've got 2.99. I'm not going to write all of these numbers. I know this is a precise number, but I'm too lazy to write this. 2.996 times 10 to the 14th electrons. Right? This is a whole number. This is less than 14 powers of 10. But it's just so many numbers. We don't really care that much about the details of how many electrons. The big idea is whole numbers of electrons are what make up total charge. And we can figure out how many electrons there are by dividing the total charge by the charge of a single electron. I think a takeaway from this also is 48 microcoulombs is actually quite a bit of charge. And so we're looking at, 3 times 10 to the 14th electrons to make up a pretty small amount of charge. It takes a boatload of electrons to make up, sort of measurable amounts of charge. All right, so moving on from my calculator problems to more physics, and I've lost my cursor. A conceptual question. So we see 2 charged balls repelling each other as they hang from the ceiling. All we know is that they're 2 separate objects and that they repel from each other. What can we conclude about the charges? If all we know is that they repel, all we can conclude is that they have the same sign charge. So they're either both positive or they're either both negative. But without more information, we can't say anything else. Next question. From the picture, so green repels pink and green repels yellow, what can we conclude about the charges? We must conclude, since everybody repels, and we're assuming that these are 2 separate scenarios, that the pink is not attracting the green over here, because that would mean green isn't green. We must conclude that all 3 have the same charge, since they all 3 repel. So a lot of this is kind of like logic, along with the idea of opposites attract and like charges repel. We'll be very interested in conductors and insulators when we start talking about DC circuits, direct current circuits. Understanding the difference between insulators and conductors is also important for charging objects, because insulators and conductors act fundamentally differently when they're charged. So a conductor is defined as a material in which charge flows freely. The reason charge flows freely in a conductor is that the atoms in a conductor have a shared cloud of electrons on the outside of them. The details, again, are more for physical chemistry or chemistry, but in general, there's sort of a valence cloud of electrons, an outer cloud of electrons in a conductor, in which the electrons aren't really stuck to a particular atom. The total charge is typically neutral, so total number of protons equals total number of electrons, but on some level, some electrons are free to move from one part of the conductor to any other part. They're free to move under the influence of an electrostatic force. Conversely, in an insulator, no charge or almost no charge, depending on the amount of push, flows. That's most other materials other than metals. For example, in the picture here, wood. So in an insulator, the difference is that the atoms, whatever their arrangement are, the atoms or molecules, hang on to their electrons. There's no sharing of electrons through any sort of shared cloud. The electrons may move in place around their particular home atoms, but they don't move from one atom to the next. So if we see a metal ball, so we're thinking metal means it's a conductor and charges can move on a metal ball. It's hanging from the ceiling by an insulating thread. And the ball is noticeably attracted, right? It moves when it's in the presence of a known positive charged rod held near the ball. What can we conclude about the charge of the ball? So we can definitely identify that the ball might be negatively charged because we know opposite charges attract. However, since charges can exert forces on each other and like charges repel and opposite charges attract, and because the ball is a conductor, if I bring a positively charged object close to this conductive ball, that positive charge is going to pull on those free to move electrons in the outer valence level of the metal. So the positive charge will attract some electrons, and those two opposite charges attract each other while the positive charge pushes, well, we could say it pushes away the positive charge. It's more like it exposes the positive charge of the nuclei on the right-hand side. And so The attraction of the positive negative, which are closer than the repulsion of the positive positive, causes the metal ball to move towards the positive charge, even if it's neutral. Trick question. Okay, so now we have two neutral conductors and they're connected by a wire, and then a charged rod is brought close but doesn't touch. Then the wire is taken away. What do you think are the charges on the conductor? So we're thinking neutral, neutral, connected with an additional conductor, and that opposite charges attract. While this positively charged rod is here, still pulling on opposite charges, we take away that path of conduction. What do you think the charges on the blue and the green balls might be? I hope you concluded that the blue ball ends up being negatively charged because the positively charged rod attracted negative charges over to the blue ball, exposing positive charges on the green ball. And then since we removed the ability for those charges to move while the positively charged rod was present, we've sort of solidified that separation of charge. This is called charging by induction. We're not going to worry too much about the details because I haven't seen questions like this on the test, but this is an interesting application of charges being movable in a conductor compared to an insulator. Here's a bigger picture of what's going on. If I bring a positively charged object next to a conducting object, even if that conductor is neutral, the positive charge will pull on the negatively charged free-to-move electrons. The negatively charged free-to-move electrons will move as close as they can get to the positively charged object. And that will expose the protons in the nuclei of the atoms on the right-hand side of the conductor. The repulsion and attraction force has to do with distance. So the fact that the electrons and the protons here are closer to each other means that this attraction is bigger than the proton-proton repulsion. So there's a net attraction. This phenomenon occurs in conductors, but it also occurs in insulators. The difference is that in insulators, or as we're saying here, non-conductors, because why not make it as complicated as possible, the separation process is on a smaller scale in an insulator. The electrons that are attracted to the positive charge can't all move over to the left-hand side, but we can cause polarization in the atoms or molecules in the insulator. So finally, we get to Coulomb's law, the details of the attraction and repulsion between charged objects. So this is credited to Charles Coulomb in the mid to late 1800s. I'm not actually familiar with the specific experiments he did, but we're still in the 1800s, 1900s. No, excuse me, 1800s. So we're still in the realm of classical physics, even though we're considering very small particles now. We're not exactly in mechanics, but it's not yet modern physics. So the force between charged particles is found to be equal to a constant k, lowercase k, and there is a problem here because lowercase k is also used for spring constant, but it's a constant times Q1 times Q2. So these are the amounts of charge, so amounts of excess positive or negative charge on each object. The two objects are interacting, divided by r squared. The equation gives the magnitude of the force. The direction of the force is left to the user because you know that like charges repel and opposite charges attract. So you're sort of required to figure that out on your own. As we said, the unit of charge is a coulomb in honor of Charles Coulomb. Capital C is the symbol. That constant K is 8.988. I think the AP equations table gives it as 9.0 times 10 to the 9th units of newtons times meters squared divided by coulomb squared. And the charges produced by rubbing, so by a friction interaction, are typically around a single microcoulomb. So when we found in example problem number 1 that it took something like 10 to the 14th electrons to make negative 48 microcoulombs of charge, we're talking about typical charges in I lost my place. Whoops. In a situation of sort of static charging, right? So charging by contact. What else do I want to say about this equation? This equation should be eerily familiar to you. We looked at the force of gravity, the universal gravitation, credited to Isaac Newton in the 1700s. And when we did that, we said pull of gravity is equal to a constant, universal gravitation, times mass 1 times mass 2, amount of mass in each object in the interaction, divided by r squared. So the similarity here is striking. We have a constant. G is, oh boy, I think, I forgot what G is. How is that possible? And I don't remember where I put my equations table because it's the end of the term. I can see it right here, I think. Nope, that's a different paper. My equations table is blue, and that is not blue. Nope, I don't know that I have my equations table. Anyway, it's a constant, and it's like 10 to the negative 11th, right? It's something times 10 to the negative 11. Let's do proportionality here. Masses divided by distance squared. So the form is very similar. The value of the constants, however, is very different. 10 to the negative 11th compared to a k value of 10 to the 9th. So we're saying that the gravitational pull on a sort of universal scale is quite weak compared to the electrostatic force. They're both inverse square laws. That's a similarity. Gravitational pull, as far as we know, is only attractive, whereas electric force can be either attractive or repulsive depending on the sign of the charge. So as I said, the direction of that force is determined by you, by the user, knowing that like charges repel and opposite charges attract. This is an interaction force, and just as we talked about for gravitational force, that M1, M2 is interchangeable. So the force of mass 1 on mass 2 is equal to the force of mass 2 on mass 1. Same story. The force of charge 2 or charge 1 on charge 2 is equal and opposite to the force of charge 2 on charge 1. We're consistent with Newton's third law of action-reaction. So let's try some ideas about Coulomb's law. What is the magnitude of force F2? I hope you answered D. If we know F1 is 3 newtons and that force is due to the repulsion of these two charges, we must conclude that F2 is also 3 newtons. This is a third law action-reaction pair. If we increase the left-hand charge from Q to 4Q, what becomes the force F1, 3 newtons to which? By how much does the force change? I hope you answered that the force changes by 4 times. If I increase one of the charges by a factor of 4, I need to increase the total force also by a factor of 4. I like this follow-up question. What's the magnitude of F2 in both cases? I hope you answered that F2 in the top case is 3 newtons and F2 in the bottom case is 12 newtons. Action-reaction F1, F2 have to be the same. Action-reaction F1, F2 have to be the same. The force between two charges separated by a distance d is F. What happens to the force if the charges are pulled apart to a distance of 3d? So what happens to the interaction, I should say, what happens to the electrostatic interaction force if I triple the distance between the particles? I hope you answered either D or E first, because you need to understand that as distance gets larger, force gets smaller. But specifically, of course, I hope you answered E, 1/9. If I triple the force, I don't decrease the force by 1/3, but because the distance is squared, I decrease the force to 1/9 of its original force. Now let's try a computational version of the same thing. So what's the magnitude of the force a plus 25 microcoulomb charge exerts on a plus 2.5 millicoulomb charge at 16 centimeters away. So we want to go back to Coulomb's law. The electrostatic force is equal to constant K times Q1 times Q2 divided by R squared, where R is the distance between the two. We also need to recall that K, I'm going to use the AP equation table version, is 9 times 10 to the 9th, I hope, Newton meter squared per Coulomb squared. Let me just check on that. Not knowing where my AP equation table is. Yeah, 9 times 10 to the 9th. I just wanted to make sure I had the correct power. Okay, and so we've got a Q1 of 25 microcoulombs, and we have a Q2 of 2.5 millicoulombs, a boatload of charge, and then we have a distance of 16 centimeters. And as soon as I've written these down, I notice that none of these are in SI units. So before I complete calculations, I need to rectify newtons. If I want my answer to be in newtons, I've got to be meters for distance, and I've got to be coulombs for charge. So microcoulomb, 25 times 10 to the negative 6 coulomb. Millicoulomb, 2.5 times 10 to the negative 3 coulomb. Distance, 0.16 meters. And now I can proceed with the calculation. The electric force is equal to 9 times 10 to the 9th. I'm going to drop the units because I can't fit them on this paper writing this big. Times 25 times 10 to the negative 6th coulomb times 2.5 times 10 to the negative 3rd coulomb. All of this is divided by 0.16 meters squared. Okay, and so now you get friendly with your calculator using scientific notation. Let's see if I can do this one correctly. Okay, so I'm going to use, I don't think I need parentheses, but I feel like I might need them. I'm not loving this calculator. Okay, 25 to the negative 6 and 2.5 negative 3. Okay, so across the top I have 562.5, and then I divide this by 0.16 squared. Also, again, shouldn't need the parentheses, but I'm not sure. Okay, and so I have a force of 21,972. Let's round up to 22,000 newtons. This is an extremely large force, but we've already talked about how a microcoulomb is quite a decent amount of charge, and a millicoulomb is a huge amount of charge. We have a 10 to the 9th times 10 to the 6th times 10 to the negative 3rd, and then we're dividing that by a 10 to the negative 2 squared. So this is a reasonable large force. Such a large amount of charge at a relatively close distance will exert a large amount of force. I feel like I should check the answer just to be safe, but usually we're dealing with charges interacting that are in the microcoulomb range, and instead we are finding a millicoulomb range. Something is wrong with my solutions manual though. Oh, I printed the chapter 12 solutions, or no, I'm looking at chapter 12 solutions. Well, we'll check it, and if I'm not correct, I'll come back to it. Okay. So that proportionality constant, lowercase k, can also be written in terms of epsilon naught, which is called the permittivity of free space. When in AP Physics 2, you start looking at the interaction between electric fields and magnetic fields, it will be very useful to express electric force in terms of epsilon naught, because epsilon naught is a term we use for electric field pretty specifically. And so epsilon naught is defined as 1 divided by 4 pi times the permittivity, or 4 pi times Coulomb's law constant K. And the quantity epsilon naught is equal to 8.85 times 10 to the negative 12. You notice that the units invert, because when it's K, we want to end up with newtons, and it's K is in newtons meter squared per Coulomb squared. Epsilon naught is 1 over K, so So our units invert to Coulomb squared divided by Newtons times meter squared. You should not need to use epsilon naught, but you will see both K, Coulomb's law constant, and epsilon naught on the AP equations table. But really, as I said, this is more important for AP Physics 2, moving on to looking at the interaction between electric and magnetic fields. So Coulomb's law strictly applies only to point charges. We can apply it to charged objects as long as the size of the charged object is very small compared to the distance between the charged objects. We made that same argument for the universal law of gravitation. If we have a large distance between the charges or very small charges compared to the distance between them, we can treat them as point charges, and we can find net force of collections of charges as long as we consider the force between individual pairs and we account for the direction of those forces. So these are forces. We understand that forces are vectors, and we have to worry about the direction. A reminder for adding vectors. When we're adding two forces that are acting on an object, we have to consider the vector nature. If we're doing this graphically, we can use the tip-to-tail method or the parallelogram method. I think we've discussed both. And if we need to know specifically values, which is well within the scope of this course, we have to find the components of the vectors and then add their x and y components together. You're never going to be done with this vector component thing. So let's look at some concepts, and then we'll do some examples. So a proton and electron are held a distance of 1 meter apart and then released. They're opposite signs, so they attract. As they approach each other, what happens to the force between them? I hope you answered that the force between them gets bigger. So they're attracted to each other, whatever their distance, because they're opposite charges. And so because they're attracted to each other, if they're allowed to attract to each other, they move towards each other. And as they move towards each other, that force gets bigger and bigger. So they accelerate towards each other, and their acceleration increases as they get closer. A proton and an electron are held apart a distance of 1 meter and then released. Oh, shoot, I already answered this. No, I didn't. I said that their acceleration gets bigger, right? Because the force gets bigger. Which particle at any moment has a larger acceleration? Do they have a larger acceleration? Thinking about Newton's third law, I hope you answered that the acceleration of the electron is larger than the acceleration of the proton. They each experience the same force, Newton's third law, action-reaction. But the effect of that force is not the same on the proton as it is on the electron. The effect of that force, the acceleration, also depends on their mass. And the mass of the electron is much smaller than the mass of the proton. Okay, so a proton and an electron are held a distance apart of 1 meter, and they're let go. Where will they meet, knowing all of the above? They meet closer to the proton, as we just discussed. The electron's acceleration is much larger than the proton, so the electron moves faster and moves farther every moment compared to the proton's movement. So they meet closer to the proton than they do to the electron. The extreme of this is our bowling ball dropping example. If I drop a bowling ball close to the surface of the Earth, we don't notice the Earth's acceleration up. We only notice the bowling ball's acceleration down. So now we're looking at vector addition. Here we have 3 charges interacting. We want to figure out the net force on the yellow charge plus Q. So I want you to consider plus Q yellow charge and plus 2Q green charge at a distance d, then plus Q yellow Q and plus 4Q blue Q at a distance d below. What direction do you expect the force to be? I hope you answered either B or C, because we know that both of these sets will repel. So we should have a repulsion up from the blue charge below and a repulsion to the right from the green charge to the left. So we should be in this range. However, the repulsion of the blue charge with the yellow charge is much larger, twice as large, as the repulsion of the green charge and the yellow charge. So we should have a force that's a bit more up than it is to the side, and B is the best choice. So now let's do some calculation version of the same idea. So again, we're looking at Coulomb's law. In fact, I should probably just keep my little deal right here. Now we're looking at multiple charge configurations. So for number 13, we have 6.15 millicoulombs placed at each corner of a square that is 0.1 meters on a side. So we need to sketch this first. Let's set the origin at the bottom corner. So here's X and here's Y. We have charge 1, charge 2, charge 3, and charge 4. I might as well label them. I think I just mixed my labels, but it doesn't matter. We know that each of these sides is 0.1 meter. 0.1 meter. Okay. So we want to figure out what's the magnitude and direction of the force on each charge. Let's start with the magnitude and direction of the force of each charge. Actually, let's do it at the origin. Let's find the magnitude and direction of the force, the net force of each charge on charge 3, so that we're always referring back to the origin. So what I need to know is, what is the force of charge 1 on 3? What is the force of charge 2 on 3? And what is the force of charge 4 on 3? I need to know both the magnitude and direction of each of these forces, and then I need to add the forces vectorially. That's going to be our answer for any of the 4 charges. And I think we only need to do it once to see the example. So the force of charge 1 on 3 is going to be equal to charge 1, K, times charge 1 times charge 2. And the charges are all the same. The charges are all 6.15 millicoulombs. So 6.15 times 10 to the negative 3 coulombs. And it's 6.15 times 10 to the negative 3 times 6.15 times 10 to the negative 3. So I'm just going to square that. And then that's going to be divided by the distance between these two charges. This is along the side of my square, so that's 0.1 meters squared. I'll come back to the calculation in a moment. I'm going to skip to 4 on 3 because 4 on 3 is going to be the same. I am one side away. I have K, Q1, Q2, divided by distance squared. So the quantity of force on charge, or of charge 3 on charge 1, and the quantity of force of charge 3 on charge 4 is going to be the same, but they're going to be in different directions. Then we're going to look at 2 on 3, right? 2 on 3 is not along the side, but it's along the hypotenuse of this triangle, or of this rectangle, not rectangle, square, right? And so this is going to be equal to the square root of 2 times 0.1 meters. So K, Q1, Q2 are the same, 6.15, 10 to the negative 3 coulombs squared, divided by square root of 2 times 0.1 quantity squared. That's messy, but whatever. You got it. All right? And so we calculate, we calculate, we calculate. Let's get some numbers. So again, K is equal to 9 times 10 to the 9th. Let's rearrange the paper a little bit. I'm hoping to be able to squeeze this all on the same page. So 9 times 10 to the 9th. I keep losing my power of 10 button. 9 times 10 to the 9th times, shoot, I forgot to put parentheses. I wonder if I can insert. Not a fan of this calculator, as I've said many times. 10 to the 9th, plus parentheses, then 6.15 times 10 to the negative 3. And I actually don't know how to make a square. No, will that work? Yeah, that'll work. Okay, so that's the top of my F13. And then I'm dividing that by 0.1 squared. Nope, I got a syntax error. Shoot. Because closed parentheses. Let's do that. Let's see. Whoops. Oh, shit. You guys, I am having a tough time here. Okay. Parenthesis, 0.1 squared, because I'm nervous. No, darn it. Oh my gosh. Oh, for heaven's sake. Oh, for heaven's sake. I can't win today. Let's start this party over. 9 times 10 to the 9th. I hope you're fast forwarding through my calculator problems. Times 6.15 times 10 to the negative 3, close parentheses, square that quantity, enter, tell me the number, divide that whole thing by quantity, 0.1 squared, close parentheses, enter. All right. It's a huge force because these are huge charges, 10 centimeters apart. So what is this? 3,404,000. No, it's 34 million. Okay, very good. So do we want to keep the whole thing? Why not? Sure. So this is 34. I don't know why my calculator is not giving me answers in scientific notation, and I'm already having enough calculator problems, so I'm just going to write it as there. All right, okay, so F13 is here. F43 we have identified as being the same quantity, although different direction. And then we need to recalculate for F23. All right, so K, 9 times 10 to the 9th, close parentheses, times Q1, Q2, same quantity, 6.15 times 10 to the negative 3, close parentheses, squared. If I knew how to save numbers, I would do that. Then we get the same K, Q1, Q2 across the top. But our distance is different. So I'm dividing by, oh dear, how do I do square root of 2? Square root of 2, oh geez, square root of 2, times 0.1 quantity squared. Go. And we have a smaller force because we're larger distance apart. So this is 17,020,125 newtons. All right. So the numbers are weird, right? We've got really small numbers. We've got really big numbers. We're getting friendly with scientific notation. I hope you're not having the same problems as I am with my dang calculator. All right, and so now let's get some color coding because we've got to deal with the directions. So we have yellow F13, we have pink F23, we have blue F43. We want to add these forces, but we have to deal with their vector nature. So here's my origin again. Here's the y-axis, here's the x-axis, and here's particle 3, because all 3 of these forces are acting on particle 3. So F13, the interaction between 1 and 3, 2 positively charged particles, needs to point directly down. This is F13. F34, interaction between 2 positively charged particles, has to be directly to the left, because again, they're repelling each other. And then F23 on a 45-degree angle, because this is a square, F23 is smaller than the other two. It's at 45 degrees above or below the x-axis. I mean, below the x-axis or to the left of the negative y-axis, 45, 45. And so now we need to add our vectors. So in order to add these vectors, I need to know what the x and y components of F23 are. And then I can add x and y net force to find total force. Oh, there's another way to do this. I could find the x and y components of F23, but I'm feeling lazy because it's Thursday morning of the last week of the term. I know that F43 and F13 are also going to combine to a 45-degree angle force because they're equal in magnitude. So instead, I'm just going to add these two, right? I'm going to focus on F43 and F13, knowing that they're equal sides of a square themselves, right? I'm looking for this value. And then I'll add that value to F23 because everybody's now pointing at 45 degrees below the x-axis. So F43 plus F13 is going to be equal to square root of 2 times the value of either of these lengths, right? These are the same lengths. So square root of 2 times 34,000, or 34,040,250 newtons. Sweet. So that's equal to 34,040,250 times square root of 2 is 48,140,183.2. This is now at 45 degrees. So this is now my F4313 combo, which I'm going to add to F23, and I can add these algebraically because they point in the same direction. So F net is equal to 48,140,182 plus 17,020,125. The combo of F43 and 13, 45 degrees below the x-axis, plus F23, also 45 degrees below the x-axis. 17,020,125, 65,160,308 newtons at 45 degrees below negative x-axis. Done. That was pretty complicated because once we have to deal with the direction, vector addition gets complicated. All right, let's look at our last example problem. A large electroscope. Oh, and I have not described electroscopes in the lecture. I will show you what an electroscope is in class. A large electroscope is made with leaves that are 78 centimeters long wires with tiny 21-gram spheres at the end. You know what? This is way beyond the scope of the AP test. Let's skip this. If I find AP questions that are like this, we'll come back to it. But let's go ahead and skip example 15. And then we're also going to skip the very last problem of the problems that I gave you because they're related. As I said, I'll come back to this after the break if it seems that we need to know how to do something like this. It's an interesting problem, but this lecture is already quite long. So coming back to this if needed, the end. Oh, I'm supposed to say, don't forget to smash the like button and comment or subscribe, but only comment if you're feeling positive. See you later. Have a nice spring break.